Alright, so on this next example, we can now use the horizontal and vertical components to solve problems. In this problem, Andrew pushes a 15.2 kilogram lawnmower with a force of 118 newtons applied to the handle, which makes an angle of 28 degrees with the horizontal. So we want to determine the horizontal and vertical components of the applied force. If we're drawing this to visualize, we can have the handle right there. That is right where Andrew is pushing the lawnmower. The angle he's pushing the lawnmower with, that's the handle, this is 28 degrees. So to do this as a free body diagram, we have that there. That's his applied force. That is what he's pushing down on the lawnmower with. That is a value of 118 newtons. All right, we're going to also find the horizontal and vertical components. Our horizontal component is going to go straight across, and that's going to be the applied force, but in the x direction. And then we're also going to have the applied force, but in the y direction. All right, we're also going to determine that we're going to make north positive, east positive, south positive, and west positive. All right, so let's do the applied force first for the x component. To find our applied force, we are just going to use our SOHCAHTOA tricks. So again, I'm not going to even show you the steps. We've done it a million times, but it's 118 newtons times the cosine of 28 degrees. Right, that's that angle there, is right here. This is 28 degrees. So when you plug that into your calculator, you'll find the x component is equal to 104.188 newtons. Then when we find the y component, we do the same thing we've been doing the whole time. 118 newtons times the sine of 28 degrees, and that's going to equal negative 55.398 newtons. That makes sense. The applied is heading south, which is a negative direction, and the applied on the x component is headed east, which is a positive direction. So what we drew up top, this is not an actual proper free body diagram. To draw a proper free body diagram, we are going to start with our device or our object or whatever we have, as we always do. And like we did before, we have the applied force going in that direction. We also have the force due to gravity heading down, and we have the normal force acting up. Right now the lawnmower is not going up or down vertically, so those will actually be the same. That is how we do a proper free body diagram. The type of free body diagram we want to use, though, to solve these problems, which makes it much easier, is a perpendicular. Free body diagram. So in a perpendicular free body diagram, we have our object, and as before, we are going to have our normal force and our force due to gravity. But instead of moving this applied force at an angle, we are now going to have our force applied in the x direction and the force applied in the y direction, or our horizontal and vertical forces being applied. Alright, so the last part of the question wants us to determine the acceleration of the lawnmower. If we look here at our equation, we have F net is all the forces acting on it. But again, we have the normal force and the force due to gravity. Now that I drew this poorly, but with the force due to gravity, the force applied, and the normal force, right now that's all balanced. The lawnmower is not going up and down, it's staying flat on the ground. So those actually we don't include. They balance out to 0. The only force that's not balanced, that's bigger, is the applied force in the x direction. So the net force is equal to the horizontal applied force, or the applied force in the x direction. From here, we can determine force is equal to mass times acceleration, and the applied force in the x direction is equal to the applied force times the cosine of the angle. That is what we've been using the whole time to find the x component of the applied force. So when we rearrange, acceleration is equal to 118 newtons times the cosine of 28 degrees divided by the mass, 15.2 kilometers. So the acceleration of the lawnmower is going to equal 685 meters per second squared. The only direction that it's heading is forward. So it's headed forward.